Alright, so this will be our last notes in similar triangles, and then we'll be ready for a second test. We'll take the initial test on similar triangles this Friday, and then we'll add this, take a shorter test with some of the things we took in the first test, and then we'll be done with Chapter 7 and start working on Chapter 8, and try to get that done before we leave for our next trek. So this one is called Parts of Similar Triangles. Now we've been looking at some of those already before, and some of the rules, the mid-segment of a triangle theorem, and angle-angle similarity, side angle side, and side side side, and those kind of things. And now we're going to go back and look at some of the things that we, some of the definitions we learned for triangles, and now add them into how they help us determine whether triangles are similar or not. Okay. Now these special segments that we can have here, they can include something called an altitude, they can include a bisector, and they can include a median. Okay. If you remember, an altitude is just, and we'll see one right here, it's a line that goes from one vertices to an opposite side, and it forms a right angle with that side. A bisector can be is really what we're talking with an angle bisector, where if we look down here, we have a line, a segment that runs from a vertices to the opposite side, and then it splits that angle in two. So both of these angles would be congruent with each other. Okay, and then a median, let me show you that. So a median is a section that starts from a vertices and it goes across to the opposite side, and it cuts that other side into two equal halves. Okay, so AD would be congruent or equal to DC. So we're going to see how they fit into similar triangles as well. And there's something we can learn, or something we can remember to help us figure out similar triangles. So if we have these two triangles here, we have ABC with an altitude coming from A across to the section CB, and we see it's a right angle, so it's an altitude. And if we have another triangle, FGH, and then we have another altitude, because we see that right angle going across from one vertices, we can use those altitudes as similarities. So if we have these two triangles, we can say this altitude AD should be similar to altitude FG, and then we can just choose some other side, AB, FG, maybe we want to do AC or FH. Okay, and you can see the statement here for this, for altitudes and how they make triangles similar, it would say if ABC is similar to FGH, then AD, this altitude, compared to this altitude FJ, would have the same ratio as one of the sides would as well. So that's kind of the rule for similarity in altitudes. We then look at angle bisectors. They are also similar. So if we go from, if we have a triangle KLM, we have triangle QRS. If we have an angle bisector and it cuts these two angles, cuts it into an angle bisector, equal parts on both sides, or equal angles, and we can use those, and this one does the same, we can use those as ratios as well. So we can compare LP, that section, that line, to RT, and then we can compare it to some other section in the triangle like LM and RS, and they should be the same ratio. Okay, so that's altitudes and angle bisectors. So if we then look at medians as well, we can then you realize that they are also similar parts for triangles as well. So here we have this ABC, this median cuts it into two equal sections. This one XWY or Y, whatever it is, and then ZX cuts it into this triangle into two equal sides. Okay, so then we can use them. So BD and XZ have the same ratio, or be equal to, like if we did AC and YW. And we could use other sections as well. That's an example of how you can use a median as well. So altitudes, angle bisectors, and medians, they can also be used to determine whether triangles are similar as well. So then we look at one last thing here and we'll be done with the notes. This is called a triangle angles bisector theorem. So if we have some triangle bisectors, and then we can use them to figure out similar ratios, and I'll show you exactly what that means in a minute. But so the general idea is that if an angle bisector in a triangle separates the opposite sides into two segments that are proportional to the length of the other two sides. Okay, so if we have an angle bisector right here, this JM. So here he says if JM is an angle bisector of JKL, then we can realize that JK and JL, okay, will be equal to KM and LM. So the ratio between these two sides will be equal to the ratio between those two sides. So you just need to add these to your notes and be ready in class tomorrow. We'll go over some examples of how to use these in class, or at least make some videos so you can look at them if you want to, if you need further clarification, and keep adding these to your notes, and see you in class.